Hello everyone. Now we will study about complex signals. Complex signals have a real part and an imaginary part. But when we are plotting, we only plot the real part. So under these complex signals, we will study about the continuous time complex exponentials and discrete time complex exponentials. And after completing the study of complex signals, we will move to study step and impulse functions, then signal energy and power with some examples. Okay, CT complex exponentials. So we represent this continuous time complex exponential as xt equals c e to the power of at, where c and a are complex quantities. We choose to represent c in polar notation. C equals magnitude of c times e to the power of j theta, and a in Cartesian notation, a equals r plus j omega naught. So therefore you can see xt is equal to c times e to the power of j theta, e to the power of r plus j omega naught t. Then we gather the real parts of the signal and those that contain the j in the signal. So magnitude of c e to the power of rt and e to the power of j omega naught t plus theta. So you can see this e to the power of j omega naught t plus theta is a sinusoid, so that has the magnitude of 1, and this part contributes to the magnitude of the signal. So c e to the power of rt, and using Euler's relation we can write cos omega naught t plus theta plus j sin omega naught plus theta. So this contributes to the real part of the signal, and this contributes to the imaginary part of the signal. Here you can see how we have applied the Euler's relationship, and in this part is real, and this j represents that it is 90 degrees out of phase. Okay, when we had to plot, you can see we have only considered the real part of the signal, that is magnitude of c e to the power of rt cos omega naught t plus phi. So in this case, for convenience, we consider phi is equal to 0 and consider the situation where r is greater than 0. So you can see if you take the cosine part only, that cosine part varies between -1 and +1 in this fashion. Then what we are doing is we are multiplying that with e to the power of rt, where r is greater than 0. So you know that it is an exponential growth in this case. So if we draw that part only, so when t is equal to 0, it is actually the magnitude is c. So c here, and it grows like that. But since we are taking this and multiplying, so sometimes this needs to be multiplied by -1, sometimes +1. So therefore we choose to draw these envelopes, e to the power of rt envelope in blue and minus e to the power of rt envelope in blue, and then plot the cosine with the multiplication with e to the power of rt and c. So the actual signal is the red signal. So these envelopes are drawn for the convenience for us to be able to draw the signal. So you can see when r is less than 0, it is an exponential decay that is represented by c times e to the power of rt, and hence the signal looks like this. Okay. All right, now let's look at discrete time complex exponentials. In discrete time complex exponentials, xn is equal to c alpha to the power of n, and in this case c is equal to e to the power of j theta, magnitude of c times e to the power of j theta, and alpha is equal to magnitude of alpha times e to the power of j omega naught. So both are represented in the polar form. So when you put them together, you can see xn is equal to c e to the power of j theta times magnitude of alpha e to the power of j omega naught n. So therefore this n multiplies the alpha as well as j omega naught. As a result, you will have c magnitude of c times magnitude of alpha to the power of n cos omega naught n plus theta plus j times magnitude of c alpha to the power of n sine omega naught n. So therefore you can see this is the real part of the signal and this is the imaginary part of signal. So when alpha is equal to 1, sinusoidal real and imaginary parts are obtained. You can see when alpha is equal to 1, so there is no contribution to the increasing amplitude based on the time n or the integer variable n. E to the power of j omega naught n may or may not be periodic depending on the value of omega naught. So sinusoidal, exponential, step and impulse signals in combination form the cornerstone for signals and systems analysis. So that's why we studied these signals. So these come into play when we consider second order systems, continuous time and discrete time and so on. Okay, so now we want to plot this. So we once again plot the real part of the signal. So magnitude of c times magnitude of alpha to the power of n cos omega naught n plus theta, with magnitude of alpha equals to 1.12 and theta is equal to 0. So because alpha is 1.12, you can see with n it is a growing function. So once again we draw the envelopes in dotted red lines and the samples of cos omega naught n plus theta for different values of n, which they get multiplied with this, and we plot that. Okay. Then once again xn with alpha is, when alpha is less than, magnitude of alpha is less than 1.92, you can see the envelope shows an exponential decay. Alright, now let's see how to plot these signals, starting with real part of the CT complex exponential. So the real part, as we saw, is xt equals magnitude of c e to the power of j theta e to the power of r j omega naught t. So that is magnitude of c e to the power of r t cos omega naught t plus phi. So this is not the real part, this is a full signal, and we want to plot the real part of that, and that real part is this. So as usual, we load numpy and matplotlib, and then we create the plots that we want and arrange t from minus pi 3 pi to 3 pi with the interval pi divided by 100, and we take c equals 1, omega naught t equals 1, phi equals 0 and r equals 0.2. Then we construct the signal xt1 equals np absolute value of c as required here. Then np to the power of rt, that is this part over here, right here, and then the cosine part, np cos omega naught t plus phi, and there are these some commands to do the plotting. Then we will plot r equals minus 2 case as well with the exponential decay, the same signal xt2 equals np absolute value of c, np dot exp rt, np cos omega naught t plus phi. So when we plot them, you can see we obtain the real part of the complex exponentials. So if we add a phase angle, you will see this blue signal is a signal actually, does not have a maximum at 0. So maybe you can have the phase as np dot pi divided by 3, have the phase angle. If you run that, I'm sorry about that, I think it's not connected. Yeah, some minor mistakes in the code. So let me correct that. This is a version problem. So I hope it is okay now. More problems like that. Okay, so you can see because of this right here, we introduce this phase change. So compared to this signal. Okay, then comes the discrete time complex exponential signals. So C, magnitude of C times alpha to the power of n times cos omega naught n plus theta, that's the real part. So in this case, we take n values from minus 20 to 40 in steps of 1, so the integers. And we take alpha equals 1.08 and alpha equals 0.92. And for each of these, xn1 equals np absolute value of C, np absolute value of alpha to the power of n. You can see that, and np cos omega naught n plus theta. So this is alpha to the power of n. You can see that right here. Okay, so we have these plots and then some commands to get the plotting working. And you can see when alpha is equal to 1.08, it's the growing envelope, and when alpha is equal to 0.92, it's decaying. So actual signal is represented in blue in this case. These are just the envelopes. Okay. Okay, now we are done with plotting discrete time complex exponential signal as well. Now we will briefly study about the periodicity properties of discrete time complex exponentials e to the power of j omega naught n. For the CT counterpart e to the power of j omega naught t, the larger the magnitude of omega naught, the higher is the rate of oscillation in the signal. So you can think like e to the power of j1t versus e to the power of j100t. So you can see this one oscillates faster and faster. So if you take the real part, you know that you plot the cosine signal, and this is for a low frequency like 1, and when it is 100, you can see extremely fast oscillations like that. That's what this means. E to the power of j omega naught t is periodic for any value of omega naught. So whatever the value of omega naught, whether the frequency is 1 radians per second or 100 radians per second or 1000 radians per second, e to the power of j omega naught t is periodic. In discrete time, as e to the power of j omega naught plus 2 pi n is equal to e to the power of j 2 pi n e to the power of j omega naught n, so this quantity is 1 because n is an integer. See, because n is an integer, that happens. E to the power of j omega naught n, the exponential at frequency omega naught plus 2 pi is the same as that at frequency omega naught. So although C in continuous time e to the power of j omega t are all distinct for distinct values of omega naught, in discrete time these signals are not distinct, as the signals with frequency omega naught is identical to the signals with frequencies omega naught plus 2 pi, omega naught plus 4 pi, and so on. Therefore, in considering dt complex exponentials, we need only to consider a frequency interval of length 2 pi in which to choose omega naught. So as we saw that in this frequency starts to increase from 0 to pi, and then from pi to 2 pi, the frequency decreases. In dt, we increase omega naught from 0, we obtain signals that oscillate more and more rapidly until we reach omega naught equals to pi. As we continue to increase omega naught, we decrease the rate of oscillation until we reach omega naught equals to pi. So notice that e to the power of j omega n, when j pi n, that means when omega naught is equal to pi, in this case the highest oscillation, e to the power of j pi n, that means minus 1 to the power of n, so it becomes plus 1, minus 1, plus 1, minus 1, so on. That is the fastest oscillation that you can have. All right. So when we compare them in tabular form, e to the power of j omega naught t and e to the power of j omega naught n, this is the continuous time signal and this is the discrete time signal. Distinct signals for distinct values of omega naught. Here identical signals for values of omega naught separated by multiples of 2 pi. And this is periodic for any choice of e to the power of j omega naught t, but this one is periodic if omega naught is equal to 2 pi m divided by n for some integers n greater than 0 and m. In continuous time, fundamental frequency is omega naught. In discrete time, fundamental frequency is omega naught divided by m. Then fundamental period, when omega naught is equal to 0, it is undefined. When omega naught is not equal to 0, it's 2 pi by omega naught. Here in discrete time, fundamental period, omega naught is equal to 0 when omega naught is equal to 0, it is undefined. When omega naught is not equal to 0, it is m 2 pi divided by omega naught. So we have many cases where m is equal to 1, but m has to be considered. Okay, now we'll look at the step and impulse functions. Okay, this is the discrete time unit step. We'll start with the discrete time version for convenience. We represent this as un, and un is a special symbol. So we have to remember that un is a discrete time step. So this is un. So you can see un is 1 whenever n is greater than or equal to 0. It is 0 when n is less than 0. So when in this range where n is less than 0, it is 0. Here n is equal to 0, it's 1. And for all the values where n is greater than 0 also, it is 1, and this continues. Now, discrete time unit impulse or the unit sample denoted by delta n. It's a special symbol, we must know that. So this is delta n is 1 only when n is equal to 0, otherwise it is 0. So when n is equal to 0, it is 1, otherwise it is 0. Okay. All right. Now we have to see the relationship between the discrete time step and the impulse. Unit impulse is the first backward difference of the unit step sequence. So what is the meaning of backward difference? And this is the backward difference. You take un and you have un minus 1 and you subtract. So this is called backward difference. So if you want to think about forward difference is n plus 1 minus un. So these are ways of obtaining the derivative of a signal in discrete time. Okay, so I have plotted un here, and now let's plot un minus 1. This is un minus 1, so you can see at 0 the value is 0. So to obtain un minus 1, what do? You put different values to n. So let's take un equals, let's say, minus 1, minus 1. So we are considering n equals minus 1 case in this case. So that is u minus 2, and we visit this one and see, okay, u minus 2 is equal to 0. Then for n equals 0, u 0 minus 1, which is u minus 1, and we visit this signal and see, okay, u minus 1 is equal to 0. When n is equal to 1, u 1 minus 1, that is u 0. So we see u 0 is actually 1. When n is equal to 2, for example, u 2 minus 1 equals u 1, and we see that u1 is equal to 1, and so on. So you can see this is un minus 1, the time delayed signal. So when you subtract these two signals, you get delta n, because only difference is right here. Okay, so you can obtain delta n as the backward difference of un. Now another interpretation is unit step sequence is the running sum of the unit impulse. Running sum. Now notice that here we have used the dummy variable m, and m goes from minus infinity to n to obtain un. Now we have to pictorially see what this is. Okay, now I am showing the summing interval with this red shaded area. So I sum up until n. In this case, n is less than 0. So now this signal is delta m. Delta m. You can see the summing region does not capture the sample at 1. Does not capture. But when n is greater than 0, the summing area captures that sample at 1. So here the sum is 0. Here the sum is equal to 1. So you can see you can obtain un with this running sum. Okay. Now we look at discrete step and impulse as a superposition of delayed unit impulses. So we are looking this impulse as the backward difference formula, then as a running sum, then as a superposition. So here you can see we are writing un is equal to k goes from 0 to minus infinity n delta n minus k. So k goes from 0 to infinity. That means k starts with 0, 1, 2, 3, 4 up until infinity. So we can draw delta n here because this is the case where k is equal to 0, we get delta n. When k is equal to 1, we have delta n minus 1, see? And then we can draw the others also when this is actually delta n minus 1, this is delta n minus 2. So here, and then you can see when as k increases, you get delta n minus 3, delta n minus 4 and so on. So when we add them also, you will get un. Add all these things. Okay. Now let's look at the continuous time unit step function ut. So ut is defined as 0 when t is less than 0, 1 when t is greater than 0, at 0 is not defined. So you can see this is the plot of ut. When t is slightly greater than 0, it's 1. When t is slightly less than 0, it is 0. Okay. Now we would like to find the relationship between the continuous time impulse function and the unit step function. So when we plot continuous time impulse function, we plot it using an arrow of height 1. Remember, it's an arrow of height 1. So there are many relationships. So now we will start finding out what those relationships are. For that, we will define a u delta t. So u delta t means unlike ut, which rose from 0 to 1 at 0, this is ut. Let's define a gradual growth. So transition from 0 to 1 happens within this time interval delta. Okay. So u delta t approaches ut as delta approaches 0. Alright. Then let's consider the derivative of this. When you differentiate that, actually this is du delta t by dt. That's what I want to plot here. So you can see derivative is 0 here. There is no growth in the signal. Here there is a positive derivative. The slope is 1 divided by delta. And here the derivative is 0 as shown here. So, not negative, 0, 0. So 0 here, 1 over delta over there and 0 there. So delta t approaches delta t approaches delta t as delta approaches 0. But see, what is the area here? Area is 1 over delta times delta, that is equal to 1. So when delta decreases, the height will increase, width will decrease, but the area will remain as 1. So that area is represented by this one over here. It's not the height of this delta t, the height is infinity actually, but we represent the area over there. It's a very peculiar representation. So you can see now we have the formula. The continuous time unit impulse function delta t is equal to the derivative of dut by dt. So in the discrete time also we got this formula where delta n we wrote as the un minus un minus 1. Actually this is the backward difference formula giving the derivative in discrete time. So for all calculations these relationships are valid. I think I would say almost all. Xt times delta t is equal to x0 times delta t. The reason is delta t is non-zero only at t equals 0, so you can conveniently put 0 there. Xt delta t minus t0, you can see now delta t is non-zero when this argument is 0. This argument is 0 when t is equal to t0. So you can put t0 over there. Other values of xt need not be considered. Alright. Now let's look at other interpretations of relationships between the CT unit step function and unit impulse function. One relationship is ut, as you might expect, is the integral from minus infinity to t. This is the dummy variable delta tau d tau. So we can see that as we did before. So we plot this is delta tau. So taking independent variable as tau, and now our t is less than 0 and our integration range is this one. So my delta t is not captured there. So what is the integral of delta tau? It's 1, but here because of the region of integration, domain of integration, delta tau is not captured. So therefore the integral is actually 0. But if I consider this situation where t is greater than 0, this is tau. So this is delta tau that we are plotting. The integral is 1. So we can see depending on the sign of t, we get 0 or 1, which is actually ut. So you know that ut is equal to 1 when t is greater than 0, 0 when t is less than 0. So we obtain that through this. So now we look at signal energy and power. So the total energy over time interval t1 to t2 in a continuous time signal xt is defined as integral from t1 to t2 modulus of xt squared dt. So you can see when you have a resistor of R equals 1, there is a current IT and the voltage is VT. So you can see that VT equals 1 RIT. So this is equal to 1, and so therefore you can see, if you forget about the units and in signals and systems you don't consider the units, VT and IT are equal. So therefore instantaneous quantity I squared t or V squared t represents an energy. So the total energy over time interval n1 to n2 in a discrete time signal is xn modulus squared dt summation from n1 to n2. So total energy over an infinite interval in CT signal is defined as E infinity is defined as limit t goes from t tends to infinity minus t to t modulus of xt squared dt. So we can just write it as minus infinity to infinity x modulus of xt squared dt. So total energy over infinite interval in dt, a signal is limit n goes to infinity from minus n to plus n xn squared. So we can write n goes from small n goes from minus infinity to infinity x modulus of xn squared. Note that this is integral and that this integral may or may not converge. Some signals, such signals have infinite energy, while signals with E infinity less than 0 have finite energy. So infinite energy signals and finite energy signals. So finite energy signals are called energy signals. Okay, now let's consider power. The time average power over a finite interval in a CT signal is, so this interval is from minus t to t, so we divide by that interval to t. So limit t tends to infinity, 1 over 2t, integral minus t to t, modulus of xt squared dt. Total energy in dt signals is p infinity equals limit n goes to infinity. So you can see from minus n to n you have 2n plus 1 samples. So that's why you divide it by 1 over divided by 2n plus 1 modulus of xn squared. With these definitions, we can identify important classes of signals. So it's important to remember this for us. Energy signals, signals with finite total energy, that means E infinity less than 0, these have stored 0 average power. For example, if you consider a signal like this starts and it's a pulse. This has a finite energy. Power signals, signals with finite average power. P infinity is less than infinity. As P infinity is greater than 0, E infinity is infinity. So if you take a periodic signal like a cosine, horrible cosine, I'm sorry about that. So then this is a power signal. So aperiodic signals that have like a pulse, they are energy signals, and these are power signals. Signals which neither E infinity or P infinity are finite, infinite. Okay, so this is the class. So signals with neither E infinity or P infinity are finite. So these are neither energy nor power signals. So let's take some examples. So first example, determine whether the following signals are energy signals, power signals, or neither. So take this one, xt equals e to the power of minus 80 ut. So therefore a is greater than 0. Since a is greater than 0, it is an exponential decay like that. So this part we don't need to consider because we know that ut is 0 here, right? So when you multiply by ut, ut you know is like that. So when you multiply by ut, although this first they are continuing, that part gets multiplied by 0. So now let's consider this. So xt is equal to e to the power of minus 80 ut, a is greater than 0. So we use the definition of E infinity, which is limit t goes to t tends to infinity minus t to t, modulus of xt squared dt. So now we can just start integrating from minus infinity to infinity. Modulus of xt squared, so this is a real signal, so therefore modulus is that signal itself, and since we have to square it, you get minus 2at instead of minus 80. And then when you integrate, so 1 minus 1 over 2a to the power minus 80. So remember 0 to infinity is obtained because from minus infinity to 0 the signal is 0 because of the action of ut. So when you put the limits, when you put infinity, because a is greater than 0, this quantity is 0, and then when you put 0 here, it's 1, so therefore 1 over 2a. So E infinity is finite, so therefore this is an energy signal. So is P infinity finite? Of course P infinity is finite in this case. Now let's consider the second example, which is a periodic signal a cos omega naught t plus theta. So xt equals a cos omega naught t plus theta. So infinity is limit t tends to infinity minus t to t, xt squared dt, limit t tends to infinity from minus t to 2, a squared cos squared omega naught t plus theta dt. So therefore we have to apply cos squared formula with using cos 2 theta. A squared divided by 2, so there's a 2 here because of this formula, the trigonometric formula that we apply, identity that we apply. Minus t to t 1 plus cos 2 omega naught t plus 2 theta plus times dt. So therefore we have to integrate this quantity. So t cos 2 omega naught plus 2 theta divided by 2 omega naught. Then let's consider t for convenience as an integer multiple of 2 pi by omega naught. So you put 2 pi by omega naught here, so therefore that part gets subtracted off because of the property of the cosine. So therefore the answer that you get is E infinity 2 is there, so limit you get t. Oh yeah, here you get 2t, so these two 2's get cancelled off. So because you put t here and minus t over there, and then you get infinity. So therefore E infinity is infinity, so this is not an energy signal. Then to consider the power, we can take that integral we already obtained and divide it by 2t and tend that to infinity. So therefore you get a squared divided by 2, which is less than infinity. So therefore these are power signals. So you can see these periodic signals are usually power signals. Then let's consider a signal that is neither an energy signal or a power signal. So this is t, a ut. So therefore if we plot that signal, so you can see our ut is like this, our t is like this, and when you multiply them you get this growing signal that grows with time. So this part becomes 0. So when we consider E infinity, you get t dt 0 to t because of this action of the ut, and t squared divided by 2, so this t squared divided by 2, and we have infinity. This is not an energy signal. So to get the power, we divide that quantity by 2t, and then still it tends to infinity. So this is not a power signal either. Okay, so what we studied today, we studied about continuous time and discrete time complex signals, and we plotted their real parts, but these have a real part and an imaginary part. So when we consider the exponential signals, we saw that that can be exponentially growing cosine or exponentially decaying cosine in ct and dt. Then we studied about the unit step and unit impulse in continuous time and discrete time, and we saw the relationship between the impulse and the step. Then afterwards we studied about energy signals and power signals. So signals like this are usually energy signals, and periodic signals like the cosine are usually power signals. And if you have a signal that grows with time, it is neither an energy signal or a power signal. Thank you.